Calculus BC, this is a warm-up that we're going to take a look at a partial fraction problem and a differential equations problem. Take a look at number 1. We have this x all over x minus 4 quantity squared. We're going to make a partial fraction of that by saying we could have a all over x minus 4 to the first plus b all over x minus 4 to the second. What we really have to be careful about with partial fractions is that when you have a repeated factor, you've got some linear factor like x plus or minus a number, but it's raised to a power. We have to look at all possible fractions that could be raised to the first power, the second power, all the way up to wherever we stop. Here we're lucky, we only have to go up to the second power. And on the video we made this analogy. We said, look, let's just say that you had something like a 1 over 9. Let me even change it, something like 1 over 9. Of course, 9 is 3 to the second. It's very possible that you can envision fractions being added together with something with a third, something like 3 to the first, as well as something with a 9 down below. So that's why we have to do that. But in any event, I'm going to multiply through by x minus 4 squared. And we're going to get some real quick cancellations. We'll have x over here. When we multiply and distribute to this one, we'll have a times x minus 4. And right here, this cancels, and we'll just have ab. And we could either do coefficient analysis, or we could even plug in some friendly values of x. Either way would work. You could plug in x equals 4 right now, and look what would happen if you did. If you were to let x equal 4, now remember your left side has an x in it, so that would be a 4. But this a times x minus 4, that's going to completely wipe out. And in just a fraction of a moment, you can see quickly and beautifully, you have your value for b. B is equal to 4. Now, when you do this as a side to coefficient analysis, you're going to have to realize that you're going to have to do a little bit of work here. And I can even show you what's happening with the coefficient analysis in a moment as well. But let's just say that we let x equal 0. And you'd say, well, why? Well, you got to have x equaling something. Or better yet, how about x equals 5? And you can think, where in the world would you ever choose to get 5? You can let x equal whatever number you want. But you see, if you plug in a 5, the left side is a 5. Maybe you can see why I chose a 5. 5 minus 4 is 1, and 1 times a is just an a. And you have a plus b, but now you know what your b is. Your b is a 4. And you can quickly see that a would equal 1. And with coefficient analysis, what would have happened is you would have distributed, right? We did that before. And we'd say, well, this is like a 1x plus 0 on the left side. Here we'd have an ax, and then, we'd say plus negative 4a plus b. It's got a little sloppy. But the coefficient analysis would quickly show us that a would equal 1, and then negative 4a plus b, the constant, would have to equal 0. You get the same thing. You certainly get the same answer. It's just a different approach, right? So what I want to show you, though, is that what you've just found is you found what a and b are. So in green here, imagine that you're revisiting. You'd say your a, which is a 1, you'd get 1 all over x minus 4. And your b, you found to equal a 4, right? So we'd have plus 4 all over x minus 4 squared. Now we can go ahead and actually take our antiderivatives. We've broken this down. The antiderivative of 1 over x minus 4, you'd get the ln of x minus 4 in absolute value. This, though, the second part is not an ln. Remember, if we thought of this as 4 times x minus 4 to the negative 2, we'd add a 1 to get to x minus 4 to the negative 1. But then we'd have to divide by that new power also. And it would only take you a moment to rewrite it in a slightly nicer form. The 4 divided by negative 1 is a minus 4, but this x minus 4 can actually come down to the denominator, and that would be a nice partial.